Welcome to Chapter 3, where we'll be doing the same thing we did in Chapter 2, but with quantitative data. So we're going to talk about how to display, aka make pictures of, and describe, think numbers, quantitative data. So I thought I would start this off with an example to give you an idea of just how complicated this can get. So I have a table of data below from the average monthly stock prices for 6 years leading up to the financial crisis. That happened in the beginning of 2008, sort of end of 2007. And if you look at this, you want to imagine to yourself, oh my gosh, what could this data look like? So if your boss came up to you and said, hey, what's our stock price typically? You look at the table and you're like, there's some 60s, there's some 50s, there's some 70s. And he looks at you and he's like, well, or her, what's our typical value? And you're like, there's a range of possibilities that it could be, but on average, or what does it usually look like? That's hard to describe. So what we're going to look to do is take big pieces of data, this isn't necessarily big, and try to find ways to describe it well. The first way we're going to do that is by forming visuals of this. And so in Chapter 2, we talked about how charts are what we use for categorical data. We use graphs for quantitative data. And the first we're going to look at is called a histogram. Now, a histogram is just a visual way of doing this. Basically, a histogram takes your data and it creates bins or groups and counts how many of your values fall within those groups. So if you look at the graph of a histogram I have below here, in particular, you can look at one bin. Come on. Sorry, having a little bit of a pen issue. Right here, going from 55 to 60. So the idea is that, that looks like about 13-ish, I'd say. So I'd say that there are 13 values between 55 and 60. And it just gives you an idea of how often things occur, just like frequency tables were able to do for us, how often certain values occur and what those values are. And this is a part of what we call a distribution. A distribution does two things. It tells you which values there are for the variable, and how often those values occur. So it's really a twofold thing. Which values, how often? Once you have those two concepts down, or sorry, parts to your stuff, then you have a distribution. Alrighty. So besides just doing counts, just like with the categorical data, you can also do relative frequency. So you can do the percent out of total instead, and it looks the same. It's not too surprising, just like we saw with categorical data. The other thing I want you to keep in mind is that I want you to notice that these bins or boxes or the rectangles, if you will, are touching. When you're looking at a histogram, the boxes touch. And I'm writing can touch because I'm trying to be non-committal about this, because what that means is, this is a separator. If I'm below 50, I'm in this group. If I'm at 50 or above, I'm in this group, or however you decide you want to do your bins. So as you look at this, it's touching because it's quantitative data, which means they both can be right around 50. You know, I can be really close to 50 and end up below it. I can really be just above 50 or below it. Now, when you're dealing with categorical data, things like yeses and nos, you can't be on the edge of being both yes and no, because it's not a continuous range of data. So they touch. Bar charts shouldn't touch. That's a way to tell them apart. Alrighty, so the second type of display we're going to look at is what's called a stem and leaf display. Now, this is the same data, but I've taken the liberty of putting it into the stem and leaf display. So on the left, you'll notice I have the histogram from earlier. And then on the right, I have the stem and leaf display. Do they look similar? If you're having a hard time, tilt your head to the right and you'll notice that it looks about the same shape on the stem and leaf display as is the histogram. It's just a way of organizing your data. I like the stem and leaf displays because they give you the specific values, unlike the histogram. So we talked about being between 50 and 60, or sorry, 50 and 55. But you can specifically look at this grouping right here and say, so these are the values I see, you know, in between 55 and 60, or here between 50 and 55. It's a little more detailed. Okay, so how do stem and leaf displays work? We create branches or bars and make leaves, which are the units that are the lowest in what you see. So what we do is we take the first digit of the number, which we call the stem, and make it the bins. Now it says first digit here, but you can also do the first 2 digits if you're dealing with data that is in the hundreds or the thousandths. And then we create a solid line, and then we fill in the lower digits just to the left of it. So like I wrote here, the number 21 would be a 2, a line, and then a 1. So not only are you getting the values themselves, but how often they occur. So here's an example of a stem and leaf display that goes with the following data set. Notice that since 33 occurs twice, we have 2 3s in here. And that even though 6 and 8 are not technically next to each other on the number line, they appear next to each other when it comes to the stem and leaf display. And then, again, if you tilt your head, you can see the histogram. Fun times in awkward mathing. All right. So before you make a histogram or a stem and leaf display, you need to have the data be quantitative. There is one more type of display that we're going to talk about, but it also requires quantitative data. You shouldn't try to do quantitative data stuff on categorical data. So specifically, I mean, if you have something like a ranking scale, so rate your experience at your last shopping trip from 1 being the worst to 5 being the best, and then you have all the people's responses. That's categorical, not quantitative. Even though the response is numbers, you should not be trying to do a histogram with it. You should be doing a bar chart or a pie chart. So what are we going to do with distributions? Well, we're going to describe them. When you go to describe a distribution, you should be listing 3 things: its shape, its center, and its spread. We're going to go through all the possibilities for each of these descriptors. So when I say, hey, describe the shape of this for me, these are the 3 that you need to outline. 3s are a big thing with stats. I'm hoping you notice. There's lots of things that come in 3s. 3 types of variables: identifiers, categorical data, variables, and then quantitative variables. There's 3. There's lots of 3s. It's the rule of 3s. Let's talk about shape. The first thing we do with shape is we want to describe the modality or modes, or if you want, the number of peaks that occur in your data. So mode is just talking about who is the highest, how often that happens. So to be a mode, not only do you need to be a peak, but you also have to be the peak relative to everybody around you. So I'm drawing little circles around my peaks here because I notice that no one else is higher that's nearby. Don't assume this is a peak right here, because if you look nearby, there's something taller. So this graph that I have to the lower right is what I would call bimodal, because it has 2 peaks that I see, 2 clear, distinct, large values. We call it unimodal if it has 1 peak. Unimodal is really common. If it has 3 peaks, then it's called multimodal or more. It is okay for a graph to not have a modality. It could be the fact that it doesn't have any because everything's about the same. This can happen. When it does happen, if it looks like everything's relatively the same height, we call this uniform. So why is this called uniform and not unimodal? Because you might be, or bimodal, you might be like, well, this guy's higher with everybody close by. Yeah, but he's not like that much higher. Like there's definitely some values like, bins that are nearby and are just about the same height. So this is very much uniform. So again, no modes, looks uniform. It's gotta look kind of flat. Alrighty. The next thing we usually describe in shape is, form is what I like to call this. And there's going to be some distinct forms that we see. The first one being symmetry. Symmetry is the idea that you have reflectional symmetry across some horizontal axis. Vertical axis. So we're looking at, if I can find a place to basically fold the distribution in half and then it looks relatively like they line up, then we call it symmetric. If it doesn't do this, it might be a different form. There are lots of ways to be symmetric. So the one I have down below here looks very symmetric and unimodal. You can have symmetry that looks different. So I'm trying to draw you something here. Like here would be like a bimodal. Looks like a camel. It's bumpy. And then you'd put your symmetry line here. Don't think symmetry lines need to be in the center of the data. They might be somewhere else, just so you're aware. Okay. Now, if you have a tapering endpoint, so a lumpy, bigger part, and then it starts to decrease as you go off to one side. We call this a tail. So if you kind of imagine this is like a stegosaurus, you know, is it a stegosaurus that has the big thing in the middle? I might have that wrong. Dinosaur time. The direction of the tail is how we describe how this looks. So, and the skew distributions are very common in certain fields. This one that I have below, the skewed right distribution, and it's a right because that's where the tail is, you know, is more common in healthcare. Usually our costs or our patients behave like the typical values, the stuff that's in this lump. And then we have a couple that are atypical. When you're atypical, that's when usually you have lots of problems and they have a hard time diagnosing you and you end up having extreme costs and things like that. This is also how companies' incomes tends to look. You have most people raking around the same amount, and then you have your higher paid long-term employees, and maybe this is your CEO. That's what this tends to look like. The other type of skew is what's called skew left. So here I have the age of cardiac patients. I'm sorry, healthcare data is really easy to come across, so if you're not into healthcare, this is probably really boring for you. So again, I'm going to draw my dinosaur head over here because that's where his back is, and then here's the tail. So since the tail is pointing to the left, this is a skewed left. So there's two types of skews, and then there's symmetric. Those are our three major shapes. There are other shapes out there. You don't have to be one of these three. So data that can kind of look like this is housing data, aging data, usually things that are called demographics, which describe the individuals in your population, like how many people are in this age range, tend to look like this. So there you go. Now, one of the things we're going to have to look out for as we proceed through, well, the rest of statistics is what are called outliers. Outliers are ones that stand away from the body of the distribution, aka they seem to not follow the form of what we're looking at. Outliers can be from lots of different causes. They may be caused by an error in your data, like somebody misinterpreting a question that you ask, or, well, there's lots of ways to get these, or failing to measure properly. So one of the typical things you'll see with this is if you ask somebody to measure in inches and they decide that they're going to do their measurements in centimeters, one of those is going to be much larger than the other, centimeters, and therefore will cause some error in your data, specifically if the individuals do not label what they were doing. So these are things to watch out for. Now, it could be that your outlier just happens to be an unusual measurement in your data. Like if I did the heights of my entire class and I happen to have one basketball player that year and everybody else was not a basketball player, it's quite possible that I have one unusual measurement in my data set of heights, and that person, although different from everybody else, still belongs there because he's a part of my data, although he might be, unusual. In which case, this is, an informative piece of your data. That person has this special characteristic of basketball player because of their height or related to their height. Don't think this is causal. And therefore belongs there, but it still looks unusual compared to everybody else. Spotting outliers is difficult, just so you're aware. When we hit chapter 4, you'll notice just how difficult this can be. All right, so usually when we're characterizing shape, it's a judgment call. As long as you justify your reasoning pretty well and it looks right, you should be fine. And make sure that when you're doing this, you understand how your data was collected. This also will help you look out for outliers. Alrighty. So here's the AIG stock prices again. So you might look at this and be like, well, what's the average or typical value? And you might be tempted to be like, well, here's the peak, so it must be in here. Sorry, my pen's on delay. Come on. Here's the peak, it must be in there. So which one is it? Is it 65 and 70, or is it any of the values in between there? Or is it sort of like a balancing point? Because if I thought about this like I was going to paint it and fill it with paint, I would probably draw my line for where I would use about half of my paint is about here, in which case you might call it like 63. That's my typical value. Or if I imagine this had weight and was balanced, I might even draw it further over and call it like 62 or 63. It's hard to say where the average or typical value is, but we do actually have a formula for how we find the average, and we can actually calculate this from the data. So if you're looking at this and thinking, what am I talking about? Well, I'm talking about what's the typical value, what's the center of my data, and how can I decide where that center is. And there are different types of centers. I just did one of them with my painting example. So the first center we're going to talk about is the mean, which is also called the arithmetic average. This is a word you've heard before, average. Is it calculated exactly the same? Anyway, so what we do is we take all the values that we have and we divide by the number of values that are present. That's how you find an average. So if you're trying to find your average exam score amongst your 3 exams, you take all of your scores and then you divide by the number of points. I'm sorry, you take all those scores and add them and then divide by the number of tests you took, since there were three, and that would give you your exam average. Now, as you look at this, down below, I have some very important things for you. The symbol we use for mean is a Y with a bar over it. Y is usually your variable name. So Y takes the place of whatever you're talking about. So for instance, if you were looking at the age of your customers, you would write the mean age as age bar. This is why I was meant to do statistics my whole life, and I just didn't know it. This symbol right here is called sigma, and it represents the sum. Yay! Okay, so what does this say? Sum up all the y variables, whatever y happens to be, and then divide by the number of y's. Usually we use the symbol n to represent what we call sample size. This is going to come up again later. So get used to n now, because n does not go away. We use n the rest of the class. Alrighty, so we think of the mean as the balancing point of the distribution. It's where if everything had weight, aka I include all the y's and how big they are, and divide it equally amongst the size, aka the balancing point of the weight of the distribution. Yep, and that's how we find and interpret the mean. The next thing we want to look at is what's called the median. The median doesn't care about size. It just wants everything to be equal in number of measurements. So what's interesting about the median is it's often different from the mean. And the median is better at representing skewed data, or data that has gaps or outliers or possibly different unusual values or measurements in it, because it's not as affected by their size. So if you have like a CEO who's making millions of dollars and then your typical worker only makes like $30,000 a year, including your CEO, and talking about your average salary is going to make your average salary look huge because you have somebody who's really large in your measurements. Instead, it's more appropriate to use the median in that case because you have a large skew. We're going to see this as we go through a couple examples. Since the median isn't as sensitive to outliers or unusual observations, we call it resistant because the presence of those unusual measures doesn't change its value because it cares about number of data that you have, not the value that the data has. It's not affected by size. Okay, so here is the AIG volume of shares from that same time period. Excuse me. Oh, anyway, so on here I've placed the relative balancing point of this data. It's about here-ish, and that's where the mean would be. And then over here I've sort of colored this in a suggestive way to tell you where the median is, because the median, since it only cares about the number of data you have, it cares about area. So that example earlier where I was saying, imagine you had to color this in the same amount of color on each side. In light green, I have one side equivalent to what would appear in dark green, so that these are the same. This is where your median would fall, which we symbolize with a big M. And if you look at this, my two centers are different. Hey, the mean is 170.1 million, and the median is only 135.9 million. And the reason why this is so different is because if you look at this distribution, you would say that this is skewed to the right because of the right tail. And it's the skew right that's pulling the median further away from the mean. It's making it larger. The mean tends to pull towards your tail if you have a tail present because it wants to include those larger or smaller unusual observations inside of it, whereas the mean only cares about the number of values. So if more of your values fall towards the left, then it's going to stay in about the same spot rather than being affected by these very few unusual measurements that appeared on the right, making the tail. So for this reason, again, we could describe the median as being more stable or resistant to these unusual measurements. Resistance isn't a bad thing. It's not affected by things that might not supposed to be there, like an incorrect measurement. Alrighty. The next thing we're going to talk about is how the data is spread. So far, if you've been keeping track, it's shape. What does it look like? Where's the middle? And now it's how far out does it go? How is it spread out? This entirely describes what your data looks like when you're done. So the first one we're going to look at is what's called the range. It's how far your data goes from the min to the max. It's the distance of the values that your data covers. Now, I will tell you that range is a little bit of an older data spread value. It's not as used as much as it used to be. It's still useful because it does give you the range of possibilities for your data, but at the same time, it's also a little bit less useful. I've only used this when I've tried to decide how many tick marks I want on my graph. And that's about the only time I've ever used it, to be honest. So the range, a little bit old school, but still a valid calculation if you want to know how far your data goes. Alrighty. The next thing we're going to look at are what are called the quartiles. So the range may be a single value. It's not resistant because I'm hoping you noticed it had the min and the max in there, and the min and the max, or it might be really far if you have skewed data. So it's very much affected by outliers. However, there is a value that isn't. Okay, I'm going to draw a picture of this because it'll hopefully help you. And those are the quartiles. So imagine your data is a rectangle. That was supposed to be black, sorry. Imagine your data is a rectangle. So there you go. You don't care about how big it is, you've just arranged it in this big block. Anyway, the median is going to split this data into 50-50 pieces. So it falls like right here. There's your median. Okay. Now, if you additionally didn't want 50-50 pieces, if you wanted something a little bit more specific or smaller, you might split this into pieces that are quarters. I wanted a different color for that, sorry, and it doesn't want to let me. I'm loving this. Okay, there's a quarter, there's a quarter. So here I've got 25% of my data, 25% of my data, 25% of my data, 25% of my data, and since this is quarters, we call these quartiles. So here's quartile number 1, which has 25% of the data below it, 75% above it. We call the median quartile number 2, because it has 50% above and 50% below. And then quartile number 3 has 75% below, 25% above. So again, this is just keeping track of the number of data values that you have, not their value themselves, not how large they are or size. It's only order here and number. So if you have 8 pieces of data, each of your quarters will have 2 pieces of data in them, despite size. Get the idea? How spread out this is what we call the interquartile range, or the distance between your first and third quartile. And again, this is a distance, so we should treat it as such, and we usually abbreviate it IQR. Okay, so the IQR is a reasonable summary of spread because it only uses 2 quartiles of data and ignores kind of the upper and lower branches of the data. And what's nice about that is if you do have some skewed data, those upper and lower 25% might have some very unusual measures in it. By contrast, the thing we're going to look at next, which is called standard deviation, is focused on how can I account for size and distance away from the center. So I want to focus on how far I am away from the mean and what each of the values is contributing to that. So not only how far is the one that's closest from the mean, but the one that's furthest from the mean in a nice sort of combining way. So the standard deviation is only really appropriate for symmetric values. When you think about IQR, you should be thinking, oh, this is the one I want to use for skew, but the one I'm about to show you, the standard deviation and the variance, are really more for symmetric guys. So think standard deviation, symmetric. Everything starts with S, should be easy to go with. Too many S words. So many's. Okay, so the first value we're going to calculate is what's called the variance. Now, the variance is the old school way we used to do this. Variance isn't used so much anymore. Variance is going to pop back up when we're looking at stuff in chapter 4 and a couple things in chapter 7. Yeah, 7. Sorry, for some reason my mind was breaking on that one. So don't forget about the variance, but it's exactly what you might think. So back in the day when statisticians were trying to figure out a good way to find something that went with the mean as far as spread goes, they asked themselves, oh, well, let's just do average distance from the mean, or how far is everything spread from the mean on average? So they started with the idea of, oh, well, we'll do the mean and we'll see how far it is from all my values. So they started out with this idea. I'll take my values for every single data piece, that's what y is, and subtract the mean. So this is just distance from the mean. Ta-da! And then the next thing they did was they said, okay, we'll average it. So think about how we calculate the mean. We add everything up and divide by the sample size. And that's what these two pieces are doing. So they started out with just averaging it. And it came out to 0 every time, because for each and every value that you have present, the mean is there, which is averaging across all of them. And that always comes out as 0, which is horrible and not helpful. If you're wondering about the n-1, yes, I'll address that in a minute. So they were like, oh my gosh, we need to fix this. This is bad. Obviously, my distance isn't 0. That makes no sense. And then they remembered that usually when we do distance, we treat it as always positive. And that's a little bit of a problem because, well, we want to account for that some of the data is below the mean and hence would be negative when you do this, and some is above, so it would be positive when you do this. So how can I make this be a distance? And that's when they squared everything. Because distances are always positive. If you drive your car backwards, it doesn't take mileage off your car and stuff like that. So they squared everything, and that fixed the problem because it forced everything to be positive so that when they did the adding or averaging, using the sum and then dividing by the number that are present, it came out as something positive. So a couple things we're learning from this. 1, variance is always positive because of that squaring. 2, because of that squaring, it's also huge. Squaring makes things bigger. When you square 2, you get 4. It also gets bigger by a much larger factor than just, doubling or tripling. And then lastly, as you look at this, think about the variances. It's kind of bloated, but we're going to fix that problem. So originally they used the variances like, oh, this is kind of like how far we are from the mean, but it's too large because we squared everything. And we averaged everything, accounting for the fact that every time you subtract the mean away from a value, that value itself is already present in the mean, so I have one more data bit than I actually need, and that's why this is n-1. So the variance kind of stinks because it's too big, and if you have a couple outliers, it gets huge quickly. So how did they fix that problem? The way you might expect. I squared everything, it made it too big. You take the square root. So as you look at this, the name S makes sense, the name for variance, which I usually start abbreviating var. We call S squared because when you take its square root, you get the standard deviation. Standard deviation, hey, it's just the square root of S squared, which is S. So yes, that is the relationship between these two, because I'm just going to square root the variance. I really want you to think about this as average distance from the mean, and the root takes care of the bloating. Yay! I do not advocate you ever calculate this by hand on any data set that is bigger than 5 items. We will use Minitab to do this calculation because Minitab will do it in 2 seconds once you have the data in there, and it is much cleaner and there's no room for error. Because if you look at this and you have 20 data items in your set, or a sample size of 20, that is 20 subtractions to follow by 20 squares, and then you got to add all 20 items together and then take the square root after you divide and hope you don't do it wrong at any point in time, and you don't round too much as you do this, because then if you round too much, you end up with something that's really off also. Was that scary? I hope so. Use Minitab. Don't do this by hand. All right. So next up, hey, well, which one do I use? Well, as I've said before, hey, if it's skewed, it's sensitive to outliers. We really should be using the median and the IQR to report what this looks like. If it's, relatively symmetric and unimodal, then the mean and standard deviation are perfectly fine to use. If you want, you can also use the median and the IQR, just because it's nice to know more about what's going on with your data than before. I consider the IQR a little more informative than the standard deviation, just because it tells me about where 25% of my data is. Sorry, where 50% of my data is, middle 50%. Yeah. And yeah, so there's that. More information is better, but making sure that you're specific about how you use that information is the best. Okay, so if there are multiple modes and you're not really sure if you can split the data into groups, so if you have no characteristics that you might be able to separate them out by, or if you have unusual observations, I would say use the median and the IQR if you're not sure. And if you think it looks like it has some symmetry, you can probably get away with the mean and the standard deviation, but hedge your bets. If you're not sure, you can do all of them when it comes to describing them. Alrighty. Last but not leastly, we're going to talk about standardizing. Oh, this is not my last topic. There's definitely another one because I just totally screwed that up. When it comes to standardizing, really what we're looking at is I want to talk about distance from the mean, or how many standard deviations a value is away from the mean. This is called standardizing. It's also called studentizing, just so you know. And it's just a way of telling how far it's gone. So I want you to think of this like a ruler. That is not a ruler. Woohoo! Do. No one talk about my drawing skills. Okay, so couple things. So z-scores are going to tell you where a value lies in your data. So say that you ended up having, like, being located here. I'm going to call this 0, and we'll call this 1. And so then this is like 1 and 1.26. There we go. Now, is that informative as to what's going on? I don't really know. Because you should be looking at this, be like, okay, is this in inches? Is this in feet? Is this in centimeters? And it turns out that doesn't really matter because it's telling you how far away from 0 you are. Now, when you think about this as a ruler, how wide the ruler ticks are is your standard deviation, and 0 represents your mean. So as you look at this, right here is going to be your mean, and then the width of one of these is your standard deviation. That was supposed to be a scrolly. It doesn't look right. Anyway, so when we're doing values like this, we want to think of it as like number of ruler ticks. Standard deviation doesn't really give us any units because it's how far you went from the mean in standard deviations. Let's look at this. Here's the formula. Again, when you look at this numerator, you should be thinking, oh, distance from the mean and then how many standard deviations. That's why you're dividing by S. Dividing by standard deviation tells you how many standard deviations you are away from the mean. So for instance, having a z-score of a 2 indicates that the value is 2 standard deviations above the mean. Being 2 standard deviations above or below the mean is unusual. Being 3 or more above is highly unusual and just shouldn't happen most of the time. So what this is allowing you to do is to say, oh, are these unusual measurements? Are they possibly outliers compared to everybody else? Because it's asking how many standard deviations are away from the mean. The mean is the average, your typical value, and then your standard deviation is how spread out you are. And if you are really, really far away, aka really high z-score, either positive or negative, then that means you're really far away and possibly an outlier. Another thing to note about z-scores is that if your value is above the mean, it will be positive. If it's below the mean, it will be negative. So sign matters here, not just size. Okay? Let's look at an example. So if you look at a real estate analyst who gathered data on 350 recent sales, the average price of the homes was $175,000 with a standard deviation of $55,000, and the size of the house in square feet on average was 2,100 square feet with a standard deviation of 650 square feet. So you might want to ask yourself, which house is more unusual? A house that costs $340,000 or a house that's 5,000 square feet? And this is a lot of how z-scores are used. Here's 2 measurements that are different. How can I compare them? Z-scores. How far are they away from average? All right, here we go. So the 3,000 square foot house, we take its mean. So notice I'm not mixing apples and oranges. These are all monies or prices. So all the dollar sign stuff with all the dollar sign stuff, these are all dollar units. I'm not using money with square feet because that makes no sense. Don't mix units. And then all my square foot stuff is going with square foot stuff. Yeah, don't compare unlike things. Anyway, so if you calculate that first z-score, you should get a 3. If you calculate the second one, you should get 4.46. Who's more unusual? Who's farther from 0? Who's farther from the mean? Ha! The one that's 4 and almost a half standard deviations away is much farther away from the mean than the 3 standard deviations away from the mean, or the z-score of 3. So if you think about it, it's about how far away it is. It's a distance. In this case, it can also be negative, though. And the further away it is, the more unusual it is. All right. So because the z-score of 4.6 is a greater number of standard deviations away from mean, it is a more extreme value. Therefore, 5,000 square foot home, definitely more unusual than the one that was pricey, just so you're aware. This is also how, I say a lot. This is also how the school in particular can take students from different areas and compare them to each other and decide about acceptance. So if you took the ACT and your best friend in California took the SAT, those tests are on totally different scales. How do we decide what these students look like equivalently? Well, we take the mean and the standard deviations of those tests, we convert it into z-scores and ask, oh, which of you is the better scorer? That's a way you can do this. Alrighty. Whew. When it comes to summarizing data and information, one of the most useful that you can come across is what is called the 5-number summary. So going back to our AIG shares data, here's the 5-number summary for that data. So I'm hoping you notice this uses the median and the quartiles because, you know, possibility of skew. If you're not sure, it's always better to be safer. We'll use these two. And then it incorporates the min and the maximum. This is called the 5-number summary, the 5 extremes, the quartiles and the center that's stablest. Ta-da! So you can say, oh, boss person, our typical stock share value is about 135.9 million with a spread of, you know, I'm just doing this. Come on. I'm doing the IQR subtraction in my head, and it's not going well. So like 61 million spread. Sounds good, right? Right. So here's a box plot of that data. Oh boy, have you seen a box plot before? You probably have, or maybe not, depending on who you are. So I want to label this a little bit for you. Come on, pen. Having pen issues. Pen. Nope. All right, guess I'm writing this by hand. This is going to go well. So the center line that you see here, that's the median. This upper value here for the box is called Q3, your upper quartile. Down below, you see what is the lower quartile, Q number 1. Down here, you have the minimum. And then we have some issues because you're like, what's this thing right here? You know, that line. Boy, that doesn't look like it's pointing to the line. That's the maximum. But wait, there's data above the maximum. What the heck are these guys? What? I'm so confused. Okay, so the max is calculated a little bit differently than what you might have expected. The other name for this is the box and whiskers plot. The max and min used to be called the whiskers, the center part the box. Usually we just call this the box plot. These upper values are actually what we would call outliers. And different statistical software will label these in different ways. Minitab uses this little star dude, just so you know. Oh, that is a terrible version of this. It looks like an asterisk, if you know what that is. And then the maximum is usually calculated by Minitab as not the largest value, because that would be this star at the top. But instead, it's the largest value that doesn't fall within the bounds of being an outlier. So you should be asking yourself, well, how on earth is Minitab calculating these outliers then? Well, let me show you. The let me show you is on the next slide. I'm sorry. Let me go over this again. The whiskers are to show skewness. The box is the central medial 50% or middle 50%. This is the words that go with the things I just drew. Do I need to read this to you? Probably not. This is where I wish I had a class to be like, we're good. You can read. I believe you. So how do you make a box plot? Well, first you find the median, always. Median first. Then you find the quartiles. Draw those in there. And then you draw the box that connects all these to form the box for themselves. Now you need to worry about the whiskers. The whiskers are the harder part. So before you do the edges to make the max and the min, you need to figure out who's an outlier and who's not. And that's where a special formula comes in. So these are called the upper and lower fences. So we find the upper fence by doing 1.5 interquartile ranges above the upper quartile and 1.5 below the below the lower quartile. So the idea is if you're more than 150% farther away from the data than the upper or lower quartile, you're like too big. So formulatically, that's Q1 minus 1.5 IQRs up to Q3 plus 1.5 IQRs. And if you are either smaller or larger than that, then you're an outlier. So the largest value that falls within that will make your max, and the smallest value that falls within that will make your min, and then that's where you will draw your lines. These were also called the whiskers back in the day, and those will make the rest of your box. The rest of those labels should be labeled, the rest of the values should be labeled with special symbols or dots because they are outliers, and that's how you make this by hand. I will never make them by hand because Minitab will automatically do this calculation for me, woohoo, and then label them for me, which is super easy. Fantastic fun times. Okay, so here's some Wayne Gretzky data. Woohoo! And since he played 20 seasons, we're going to make some different displays of this data. The first one I'm going to make is my stem and leaf plot. So as you look at this, my stems are going to be the tens place, and then my leaves will be the ones place. So I got to go from 4 to 8 when making my stems. And here's a look at what that looks like. So I drew a key down at the bottom to help you out. I also did my stems as in 5. So as you look at this, like, and this just made it look better. If you do it with 10s, it looks terrible. So this is like 40 to 44. And then up here, it's 45 to 49, which those are 5. Well, I guess that's 4 each, sorry. And then if you're 50 or above, da, 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 da. So if you look at this data, I'm hoping you notice, some of these values are kind of far away from everybody else. I wonder if they are outliers. You also should be asking yourself, if you know anything about hockey, what could be causing this? Is this a season maybe or two where he was injured? Is this his early seasons where he wasn't as good as he was later in his career? Or was this late in his career where he wasn't as good as he was earlier in his career? There might be an intrinsic cause that's not represented here in the data. Okay. So next what we want to do is we want to find, hey, which games did he score 50% more points? Sorry, seasons, not games, than the rest of his hockey career. So we're going to create a box plot to do this. So if you want to do this by hand, since it is 20 seasons, you can split it right in half, 50-50, and figure out what your median is. So you'll have 10 above, 10 below, that makes your median. And then you can find your quartiles by doing, now I'll split that into groups of 5s. And here's how that would look. And then use that to make your box plot. Use your IQR to figure out whether or not some of these are unusual. I'm really suspicious of these two because they're so much lower than everybody else that they're probably outliers. Let's see how this looks. Hey, guess what? I was right. I love it when I'm right. I'm wrong sometimes too. It happens. So as you look at this, there is the breakdown of his hockey stuff. If you're looking at this and comparing it to the stem and leaf plot, I'm hoping you notice how similar they look. In particular, it's not too surprising that those two lower values ended up being outliers since they were so much further away from everybody else. You should actually take the time to calculate this by hand if you were interested in how that was done. I think I'm going to do a separate video on that one because this is getting pretty long. Fun times with Wayne Gretzky. Go hockey. Bobby Orr, that's my favorite. Why am I telling you this? Anyway. So what unusual features did you see when you look at that graph? So if you want to tick back a slide or go back about 10 seconds and take a look at the graph and ask yourself, what do I notice? I kind of already pointed one of them out to you. Uh-oh. Oh, hey, this looks skewed. How do I know it looks skewed? The width and distances on the right half of the distribution are, the left half of the distribution are farther away than the right half. So if I were to, this is one of the reasons why I also hate vertical box plots, because it really should be horizontal. Oh, that was too narrow. Hold on a second. So when we looked at the box plot, it looks something like this, where it was really chubby there and kind of narrow. And then we had some stars over here. So since this distance right here is so much wider spread than this distance, my lower 50% is spread out across a wider area. That to me just screams, hey, I'm going to be skewed left. So down here was like 40. And up here was like 80-ish. So remember, this right here is spread out very far, but it's still 50% of our data, the lower 50%. And this right here is the upper 50%. So compare your distances. Are they about the same? If they're about the same, then you're symmetric. So there's a couple different ways you could do this. You could do the middle 50%, 25% compared to the middle 25%, and then compare your lower and upper 25% to each other and ask, are these distances different? If they're more spread out to one side, or if that distance is longer on one side, you are definitely looking at some skew stuff. Remember, tail points towards skew. If it's lower values, then you are looking at a left skew. If it's higher values, you're looking at a right skew. The other thing you should ask yourself is, oh, are there any other unusual things? Well, yeah, I had some outliers. And there's a huge gap that separates these two. So, you know, the range isn't very far, but at the same time, the IQR is kind of tiny, if you care. Anyway, so that's how we're going to look at box plots and tell, is it skewed? Always watch where that tail is. You get in trouble because of tail. Okay. So when you're looking at data and trying to decide patterns, be careful. If you split the data into smaller groups and display their histograms for each group, you might know something different in trends, especially over time periods. So if you separate the AIG data into years, you'll notice some differences. For instance, one of these is way more skewed than the other. The other thing I want you to pay close attention to when you look at these graphs is I have them on the same scale. My horizontal values go from 50 to 80, yeah, 50 to 80 roughly, and then my vertical values go from 0 to 50. Since they're on the same scale, it's much easier to compare them to each other. So I'm hoping you notice one of these looks skewed. They both look relatively unimodal. I mean, we got this lumpy guy right here who's a little suspicious. You might call it bimodal for that reason. I wouldn't, just because he's not peaky compared to everything else, because this value is kind of close to him and nearby. When I say close, his height is close, and he's close in horizontal distance. So I wouldn't call him a peak. And if you look at the 2002 prices, they look fairly symmetric, unlike the data from 2003. Oh, excuse me, which looks skewed to the left. Oh. I also, if I was describing these, I would notice that it appears that the 2002 data is spread further than the 2003 data, and the center of the 2002 data appears to be higher than the 2003 data. I would call the center of the 2003 data probably like here-ish, whereas 2002 will be about here. So when you're comparing, think about the things you know: shape, center, spread, the big three. Histograms are great, but only really work for when you have two groups. If you have more than two groups, you should be using box plots because they're going to give this a little bit more representative to you. So when you're looking at box plots, you should be thinking the same thing: shape, center, spread. Okay, so I look at all these as far as shape goes. They all look fairly symmetric to me. It looks about the same from top to bottom. Not all of them are perfect. There are a few that are a lot less symmetric than others. I have no idea what this sucker's doing. You know, 2009 appears to be a weird year across the board for this scale. In fact, you probably should use a different scale. Oh, no, wait, 2009 I think is where it became worth nothing. Oh, that makes sense. Sorry, brains. The other thing you should notice is that when you're describing the next piece, the center, you can say that all of my centers are about the same for the years 2002 through 2007, but in 2008 you have an extreme drop in your center for your daily closing prices. The other thing to notice is that your spreads are all about the same for those years as well. So when you look at the centers, you're like, oh, they're somewhere between 60 and 70 for all those years, and the spread is about 5 units at max, maybe, you know, anywhere from 3 to 5 units, not too different. But when you get down to 2008, my median price, my center is down in the 30s. My IQR is like 40. It's huge compared to the rest of them. So there's where you see a severe difference in these two. In these groups. So again, shape, center, spread. The other thing worth noting is you could say, oh, well, it appears in 2003, 2004, and 2007 we have outliers. In no other cases do we have outliers. Is there something different about those 3 years compared to everybody else? Was there a big product launch? Was there something else that was going on? So ask yourself those questions. If the data appears to be telling you something is unusual happening, there might be a reason why besides just, oh, that's just what the values were. Okay. So what happened in 2008? This is kind of a fun graph. I'm sorry I'm giggling about this horrible decline into nothing. Well, the stock just plummeted. If you compare by month, here's what the stocks look like. Again, their spread is always about the same until you hit the disastrous month of September, which is where things started to go to pot. And then after September, you know, there was nothing left for AIG. You know, there you go. Medians completely decrease until they hit 0. Spreads are about the same. However, the closing month in which AIG stopped being operational is the greatest spread out of all of them. Still shape center spread. Still looks pretty symmetric through all these, except for month number 9. That's the one where, you know, it looks pretty skewed to me. And I would say that it's skewed to the right because the tail, or the larger part, appears to be on the higher values. So again, higher values, you should think about turning this and flipping it over. So I have low values to high values. So like low, that looks horrible. That doesn't look a thing like it. Let me try this again. It looks like this if you flip it towards which direction your data goes. So this is close to 0, and this is close to like 35. So again, try to imagine it on a number line, because that will help you picture which direction your skew is. Oh, here's the larger part. That's right. Okay. Let's do an example comparing downloads. So I've decided let's get some new data. AIG has been beat to death. Let's try something different. So this is looking at a number of downloads at different time periods for a new music album that was recorded over a 24-hour period. Fun facts. Let's see how this looks. So we want to compare the AM and PM downloads to each other, and we're going to display this in some side-by-side distributions to summarize what's going on. Alrighty. So here's 2 box plots. So what do we notice here? Oh my gosh, they look different, right? The morning ones have some very different behavior from the PM ones. So I'm hoping you notice the first thing you look at them and see is that, oh, well, sorry. Pause time. Sorry about that. So we're going to go through awkward laughing. We're going to go through shape, center, spread. I'm going to start with center in the description over here in words that I'm going to go through verbally with you right now. So first thing I noticed spread-wise is that, oh, the PM group, the green guy, looks very symmetric, almost perfectly so. So that's very different from what I see in the PM, or sorry, the AM purple. I really should have done PM as purple. That would have made more sense. It appears to have some skewing happening, but it's very slight. It looks almost symmetric if you look at the lower quartile and the upper quartile as compared to, so the medial 50% looks pretty symmetric. But when you compare the, hold on, let me write on this so you know what I'm talking about. When I compare the lower quartile here to the upper quartile here, the spread is clearly much larger on the larger side. So this would be a right skew, but it's very slight because these two look about the same distance-wise. It's sort of a, you know, severe but not severe kind of situation because it only is happening on half of what's going on. The next thing I would look at is that their medians are definitely very different. This one looks to be about 13 or 14, and then the median for the PM number of downloads appears to be about 23 or 22. So they're very different in that distance as well. So it appears that their spreads are also quite different. So again, I just did shape, I just did center. Let's talk about spread. If I look at the IQR for the PM downloads, it looks to be about 7, whereas the IQR for the AM downloads, that looks to be about 15. Yeah. 10, 20, yeah, about 15. 5, 10, 15, a little bit less than 15, maybe 13. So shape, center, spread, definitely very different. Notice that when you are doing box plots, this has nothing to do with the number of downloads that you have in total, because you definitely have more in the AM than you do in the PM. Or wait, hold on. If you total this out, who would it be more? It's hard to tell. You can't actually. Fun times. All right. So what do you do with outliers? Well, it depends on the context. Everything that we do in this class is all about the context. If you look at that data value in particular and it's different from everybody else and it's not informative or helpful with your data, then you should disclude them. Think about my example with the student that just happened to be a basketball player. He's still a part of my class. That doesn't mean I should disclude him just because he's tall. Taken into context, I would include that outlier. Other outliers might be something that's more important and or significant and should be removed for those different reasons. So you should always investigate, be suspicious, be skeptical, figure out, is this unusual for a good reason, or is it just a bad measurement and we need to fix it, or is it something that's just completely off the wall and doesn't really happen all that often, and that it should be excluded from your data, like a 1,000-year flood or something like that. Alrighty. Let's look at an example with real estate, a little bit different here. So if you look at a small town in Virginia, I'm rounding everything to the nearest 1,000 to make this a little bit easier. We're going to take this data and write out a couple of sentences describing the housing prices for this town. I'm hoping you immediately have some red flags being thrown up about one of the values in particular that's showing up in this data set. So when I approach a problem like this, what I would do is I would write out my data or type it all into Minitab. In order or order it myself, and then try to summarize what I see. Again, thinking shape, center, spread. Those are our ways of describing data. So if you do a histogram of this data, it's a little bit more informative than the box plot, because I have the box plot on the right, and I'm hoping you notice that this just looks crazy. You clearly have an outlier that's just way beyond what's happening with your data. I mean, look at that sucker. It's so far from everybody else that this looks squashed. So either this is a incorrect piece of data, like somebody put a decimal place in somewhere wrong, or it could be the fact that you have one house that's across like 400 acres and it's just worth way more than the rest of them, you know, small town, and then giant mansion, farm, crazy house right next door. That could be causing this. It's my suspicion that it's an error because it's just so far from everything else. And if you check the internet, it actually is a clear mistake. Yay! So you shouldn't have been using that data piece, and you should remove it or correct it. And then you'll get a lovely graph. Watch out for outliers, man. They're weird. All right. So if the distribution is strongly skewed to the right, we should be using the median. If you calculate the median using Minitab, you get about 160,000. The minimum is 122,000 without the outlier, obviously. And then the maximum is 330,000. Our middle 50% lies between 144,000 and 500,000. So that gives us an IQR of 68,500, which makes kind of sense. So as you look at where these are located at, the median is about here. That was supposed to be in red, so it was easy to see. And then our spread is about 68,000 in each direction. Yes, this definitely has some skew to it, and that's why we're using the median. All right. So what could go wrong? Don't make histograms of categorical stuff, because histograms only work for quantitative things. Yay! Remember, they're touching for a reason. Touchy, touchy, boxy makes histogrammy. Make sure you use an appropriate scale for your data. Don't make inconsistent scales. If you see any graphs where they have a starting line at 0 and then some scribbles, and then it starts doing like 50,000, 60,000, or sorry, 6,000. I'm just trying to make this work. This distance is clearly not the same as this distance. And you really shouldn't be doing that because it can really skew up your data and make it look wrong. Label clearly. You shouldn't do bad graphs. You know, do a reality check before you do your summaries. Don't be using the mean when it's something really super skewed. Don't try to do numerical summary stuff, aka means, standard deviations, ranges on categorical stuff, because it doesn't make sense. Watch out for multiple modes. If a data has multiple modes, be careful about separating the data. One of the typical examples of this you're going to see as we do Minitab this week is I'm going to do height data with men and women. Clearly, women on average are a different height than men, so it makes sense to separate those two. Watch out for outliers. They could have a very reasonable cause, or they could not belong at all. You've been warned. All right, so what did we learn? Hey, how to make histograms. They're kind of fun. We're going to do this mostly automatically. When it comes to describing the shape of distribution, we should be looking for the following things. What's the shape of the distribution? Does it have any outliers? What is the center? What is the spread? When it comes to doing centers, we should talk about the mean or the median. Those are our two types of center. They are very different. One is about where the center is accounting for value. One is where the center is accounting for number of data pieces. The next thing you should be aware of is that if you're doing those centers, you should go with the spreads that actually go with them. So standard deviation going with mean, IQR going with median. Standard deviation we want to think of as the average distance from the mean. IQR is the middle 50%. When it comes to skew, IQR and median. When it comes to things that look relatively symmetric, standard deviation and mean. Alrighty. Lastly, when we're comparing different data types, or sorry, different pieces of data that maybe have different shapes, different means, different standard deviations, we can use z-scores to talk about how far away they are from average. Remember, z-scores have no units, but their sign being negative or positive tells you which direction they are in. And we think of these as a distance, and they're a basic concept we're going to use like a lot later to do some very interesting things, especially when we hit chapter 7. Alrighty. The last type of graph we learned was called the box plot. I'm not gonna lie, I love box plots because I think they're a little bit more useful. Not to saying that, if you love histograms, I hate you. That's not at all what's going on. When it comes to the box plot, watch out for how you label the min and the max, because you should really be doing your 1.5 times the IQR to find your upper and lower fence first before you determine who's the min and who's the max. So be careful. And the 5-number summary is super useful in comparison to the box plot. All right, lastly, when it comes to comparing distributions, go through what we do when we describe distributions. Shape, center, spread. Who's unusual? Are there any outliers? That's about all. Alrighty. If you have more than 2 groups, also use a box plot instead of a histogram, because it gets messy when you have multiple histograms, as we'll see when we hit chapter 4. That's about all I have for you. Hope you're having an awesome day. Peace out.